An ion thruster is a form of electric propulsion used for spacecraft propulsion that creates thrust by accelerating ions with electricity. The term is strictly used to refer to gridded electrostatic ion thrusters, but may often more loosely be applied to all electric propulsion systems that accelerate plasma, since plasma consists of many ions. Ion thrusters are categorized by how they accelerate the ions, using either electrostatic or electromagnetic force. Electrostatic ion thrusters use the Coulomb force and accelerate the ions in the direction of the electric field. Electromagnetic ion thrusters use the Lorentz force to accelerate the ions. In either case, when an ion passes through an electrostatic grid engine, the potential difference of the electric field converts to the ion's kinetic energy. Ion thrusters have an input power spanning 1 to 7 kilowatts, exhaust velocity 20 to 50 kilometers per second, thrust 25 to 250 millinewtons and efficiency 65 to 80%. The Deep Space One spacecraft, powered by an ion thruster, changed velocity by 4,300 meters per second while consuming less than 74 kilograms of xenon. The Dawn spacecraft broke the record, reaching 10,000 meters per second. Applications include control of the orientation and position of orbiting satellites and uses a main propulsion engine for low-mass robotic space vehicles. Ion thrusters are not the most promising type of electrically powered spacecraft propulsion. The ion drive is comparable to a car that takes 2 days to accelerate from 0 to 60 miles per hour. A real ion engine's technical characteristics, and especially its thrust, are considerably inferior to its literary prototypes. Technical capabilities of the ion engine are limited by the space charge created by ions. This limits the thrust density. Ion thrusters create small thrust levels compared to conventional chemical rockets, but achieve very high specific impulse, or propellant mass efficiency, by accelerating their exhaust to high speed. However, ion thrusters carry a fundamental price. The power imparted to the exhaust increases with the square of its velocity while thrust increases linearly. Chemical rockets, on the other hand, can provide high thrust, but are limited in total impulse by the small amount of energy that can be stored chemically in the propellants. Given the practical weight of suitable power sources, the accelerations given by ion thrusters are frequently less than 1/1000th of standard gravity. However, since they operate as electric motors, a greater fraction of the input power is converted into kinetic exhaust power than in a chemical rocket. Chemical rockets operate as heat engines, hence Carnot's theorem bounds their possible exhaust velocity, due to their relatively high power needs. Given the specific power of power supplies and the requirement of an environment void of other ionized particles, ion thrust propulsion is currently only practical on spacecraft that have already reached space, and is unable to take vehicles from Earth to space. Spacecraft rely on conventional chemical rockets to initially reach orbit. Origins. The first person to publish mention of the idea was Konstantin Tsiolkovsky in 1911. However, the first documented instance where the possibility of electric propulsion was considered is found in Robert H. Goddard's handwritten notebook in an entry dated September 6, 1906. The first experiments with ion thrusters were carried out by Goddard at Clark University from 1916–1917. The technique was recommended for near-vacuum conditions at high altitude, but thrust was demonstrated with ionized air streams at atmospheric pressure. The idea appeared again in Hermann Oberthsweger's Raumschifffahrt, published in 1923, where he explained his thoughts on the mass savings of electric propulsion, predicted its use in spacecraft propulsion and attitude control, and advocated electrostatic acceleration of charged gases. A working ion thruster was built by Harold R. Kaufman in 1959 at the NASA Glenn Research Center facilities. It was similar to the general design of a gridded electrostatic ion thruster with Mercury as its fuel. Suborbital tests of the engine followed during the 1960s, and in 1964 the engine was sent into a suborbital flight aboard the Space Electric rocket. Test 1. It successfully operated for the planned 31 minutes before falling back to Earth. This test was followed by an orbital test, SERT-2, in 1970. An alternate form of electric propulsion, the Hall effect thruster, was studied independently in the US and the Soviet Union in the 1950s and 1960s. Hall effect thrusters had operated on Soviet satellites since 1972. Until the 1990s they were mainly used for satellite stabilization in north-south and in east-west directions. Some 100 to 200 engines completed their mission on Soviet and Russian satellites until the late 1990s. Soviet thruster design was introduced to the West in 1992 after a team of electric propulsion specialists, under the support of the Ballistic Missile Defense Organization, visited Soviet laboratories. General description: ion thrusters use beams of ions to create thrust in accordance with momentum conservation. The method of accelerating the ions varies, but all designs take advantage of the charge-mass ratio of the ions. This ratio means that relatively small potential differences can create very high exhaust velocities. This reduces the amount of reaction mass or fuel required, but increases the amount of specific power required compared to chemical rockets. Ion thrusters are therefore able to achieve extremely high specific impulses. The drawback of the low thrust is low spacecraft acceleration, because the mass of current electric power units is directly correlated with the amount of power given. This low thrust makes ion thrusters unsuited for launching spacecraft into orbit, but they are ideal for in-space propulsion applications. Various ion thrusters have been designed and they all generally fit under two categories. The thrusters are categorized as either electrostatic or electromagnetic. The main difference is how the ions are accelerated. Electrostatic ion thrusters use the Coulomb force and are categorized as accelerating the ions in the direction of the electric field. Electromagnetic ion thrusters use the Lorentz force to accelerate the ions. Electric power supplies for ion thrusters are usually solar panels, but, at sufficiently large distances from the Sun, nuclear power is used. In each case the power supply mass is essentially proportional to the peak power that can be supplied, and they both essentially give, for this application, no limit to the energy. Electric thrusters tend to produce low thrust, which results in low acceleration. Using 1 gram is 9.81 meters per square second. F equals ma equals F per meter. An NSTAR thruster producing a thrust of 92 millinewtons will accelerate a satellite with a mass of 1,000 kilograms by 0.092 n. 1,000 kilograms equals 0.00092 meters per square second. Thrust equals 2 *k to * power, where thrust is the force in Na, to is the efficiency. A dimensionless value between 0 and 1 power is the electrical energy going into the thruster, and Wg is a constant. The acceleration due to gravity 9.81 meters per square second ISP is the specific impulse in S electrostatic ion thrusters. Gridded electrostatic ion thrusters. Gridded electrostatic ion thrusters commonly utilize xenon gas. This gas has no charge and is ionized by bombarding it with energetic electrons. These electrons can be provided from a hot cathode filament and, when accelerated in the electrical field of the cathode, fall to the anode. Alternatively, the electrons can be accelerated by the oscillating electric field induced by an alternating magnetic field of a coil, which results in a self-sustaining discharge and emits any cathode. The positively charged ions are extracted by an extraction system consisting of 2 or 3 multi-aperture grids. After entering the grid system via the plasma sheath, the ions are accelerated due to the potential difference between the first and second grid to the final ion energy of typically 1 to 2 keV, thereby generating the thrust. Ion thrusters emit a beam of positive charged xenon ions only. To avoid charging up the spacecraft, another cathode is placed near the engine, which emits electrons into the ion beam. This also prevents the beam of ions from returning to the spacecraft and cancelling the thrust. Gridded electrostatic ion thruster research. NASA Solar Technology Application Readiness 2.3 kilowatts, used on 2 successful missions. NASA's Evolutionary Xenon Thruster 6.9 kilowatts, flight qualification hardware built. Nuclear electric xenon ion system. High-power electric propulsion 25 kilowatts. Test example built and run briefly on the ground. EADS radio frequency ion thruster. Dual stage 4 grid. Hall effect thrusters. Hall effect thrusters accelerate ions with the use of an electric potential maintained between a cylindrical anode and a negatively charged plasma that forms the cathode. The bulk of the propellant is introduced near the anode, where it becomes ionized, and the ions are attracted towards the cathode. They accelerate towards and through it, picking up electrons as they leave to neutralize the beam and leave the thruster at high velocity. The anode is at one end of a cylindrical tube, and in the center is a spike that is wound to produce a radial magnetic field between it and the surrounding tube. The ions are largely unaffected by the magnetic field, since they are too massive. However, the electrons produced near the end of the spike to create the cathode are far more affected and are trapped by the magnetic field, and held in place by their attraction to the anode. Some of the electrons spiral down towards the anode, circulating around the spike in a Hall current. Field emission electric propulsion. Field emission electric propulsion thrusters use a very simple system of accelerating ions to create thrust. Most designs use either cesium or indium as the propellant. The design comprises a small propellant reservoir that stores the liquid metal, a narrow tube or a system of parallel plates that the liquid flows through, and an accelerator about a millimeter past the tube end. Cesium and indium are used due to their high atomic weights, low ionization potentials, and low melting points. Once the liquid metal reaches the end of the tube, an electric field applied between the emitter and the accelerator causes the liquid surface to deform into a series of protruding cusps. At a sufficiently high applied voltage, positive ions are extracted from the tips of the cones. The electric field created by the emitter and the accelerator then accelerates the ions. An external source of electrons neutralizes the positively charged ion stream to prevent charging of the spacecraft. Electromagnetic thrusters. Pulsed inductive thrusters. Pulsed inductive thrusters use pulses of thrust instead of one continuous thrust, and have the ability to run on power levels in the order of megawatts. Pits consist of a large coil encircling a cone-shaped tube that emits the propellant gas. Ammonia is the gas commonly used in pit engines. For each pulse of thrust the pit gives, a large charge first builds up in a group of capacitors behind the coil and is then released. This creates a current that moves circularly in the direction of J-theta. The current then creates a magnetic field in the outward radial direction, which then creates a current in the ammonia gas that has just been released in the opposite direction of the original current. This opposite current ionizes the ammonia and these positively charged ions are accelerated away from the pit engine due to the electric field J-theta, crossing with the magnetic field Br, which is due to the Lorentz force. Magnetoplasma dynamic, lithium Lorentz force accelerator, magnetoplasma dynamic thrusters and lithium Lorentz force accelerator thrusters use roughly the same idea, with the LILFA thruster building off of the MPD thruster. Hydrogen, argon, ammonia, and nitrogen gas can be used as propellant. In a certain configuration, the ambient gas in low Earth orbit can be used as a propellant. The gas first enters the main chamber where it is ionized into plasma by the electric field between the anode and the cathode. This plasma then conducts electricity between the anode and the cathode. This new current creates a magnetic field around the cathode, which crosses with the electric field, thereby accelerating the plasma due to the Lorentz force. The Lilfer thruster uses the same general idea as the MPD thruster, except for two main differences. The first difference is that the Lilfer uses lithium vapor, which has the advantage of being able to be stored as a solid. The other difference is that the cathode is replaced by multiple smaller cathode rods packed into a hollow cathode tube. The cathode in the MPD thruster is easily corroded due to constant contact with the plasma. In the Lilfer thruster, the lithium vapor is injected into the hollow cathode and is not ionized to its plasma form, corrode the cathode rods until it exits the tube. The plasma is then accelerated using the same Lorentz force. In 2013, Russian company The Chemical Automatics Design Bureau successfully conducted a bench test of their magnetoplasma dynamic engine for long-distance space travel. Electrodeless plasma thrusters. Electrodeless plasma thrusters have two unique features: the removal of the anode and cathode electrodes and the ability to throttle the engine. The removal of the electrodes takes away the factor of erosion, which limits lifetime on other ion engines. Neutral gas is first ionized by electromagnetic waves and then transferred to another chamber where it is accelerated by an oscillating electric and magnetic field, also known as the ponderomotive force. This separation of the ionization and acceleration stage gives the engine the ability to throttle the speed of propellant flow, which then changes the thrust magnitude and specific impulse values. Helicon double-layer thruster. A Helicon double-layer thruster is a type of plasma thruster, which ejects high-velocity ionized gas to provide thrust to a spacecraft. In this thrust design, gas is injected into a tubular chamber with one open end. Radio frequency AC power is coupled into a specially shaped antenna wrapped around the chamber. The electromagnetic wave emitted by the antenna causes the gas to break down and form a plasma. The antenna then excites a helicon wave in the plasma, which further heats the plasma. The device has a roughly constant magnetic field in the source tube, but the magnetic field diverges and rapidly decreases in magnitude away from the source region, and might be thought of as a kind of magnetic nozzle. In operation, there is a sharp boundary between the high-density plasma inside the source region, and the low-density plasma in the exhaust, which is associated with a sharp change in electrical potential. The plasma properties change rapidly across this boundary, which is known as a current-free electric double layer. The electrical potential is much higher inside the source region than in the exhaust, and this serves both to confine most of the electrons and to accelerate the ions away from the source region. Enough electrons escape the source region to ensure that the plasma in the exhaust is neutral overall. Microwave electrothermal thrusters. Under a research grant from the NASA Lewis Research Center during the 1980s and 1990s, Professors Martin C. Hawley and Jess Asmussen led a team of the following engineers from Michigan State University in developing a microwave electrothermal thruster. Terence J. Moran focused his work solely upon a diatomic gas, primarily hydrogen, modeling collision-induced heating in a non-equilibrium environment for a weakly ionized plasma with less than 0.1% ionization. He combined the use of statistical mechanics and kinetic theory. Using the Boltzmann-based kinetic theory of gases, he applied simple chemical reaction models of plug-flow reactor and continuous stirred tank reactor models. Randall A. Chapman conducted many experiments using a microwave cavity system. His research focused on hydrogen gas at low pressures and at low microwave power. He showed a 20% net power absorption to the exiting gas from the cavity system, calculated a vibrational temperature range of 4,000 to 17,000 Kelvin, and measured an ionization percentage of between 0.001 and 0.1%, which demonstrated that the electron density increased with pressure and energy. Stanley J. Whitehair obtained experimental measurements of microwave coupling efficiencies, thruster energy efficiencies, and specific impulses for nitrogen and helium propellants over discharge pressures ranging between 40–1100 torr with varying propellant flow rates. With efficiencies in excess of 95%, he established that the MET is a very efficient thruster. However, he noted that melting and erosion of the nozzles limit the input power and specific impulses. Scott S. Haraburda developed a simple equilibrium-based theory of space-dependent parameters for transport design equations, using helium as the monatomic gas and nitrogen as the diatomic gas, applying the finite element method within the plasma in a batch reactor model of the TM011 and TM012 electromagnetic resonance modes of a microwave cavity. He predicted the residence time of the reaction to equilibrium. With his data, he conducted many simulations on NASA's two-dimensional kinetic computer program to determine the effects on engine performance from pressure and energy changes along with propellant contamination. He determined that one should use a minimum power of 1 kW to obtain specific impulses greater than 1000 lbf*sec pound. He also determined that fouling of the walls in the discharge chamber significantly reduces the amount of energy transferred to the propellant, thus reducing the rocket efficiencies. Comparisons. The following table compares actual test data of some ion thrusters. The following thrusters are highly experimental and have been tested only in pulse mode.